Question. This is our last question of part A. Yeah. After we finish this question, we will move to part B. Yeah. All right. So now we have this system, yeah, network. Yeah. We need to find I1 function, I2 function. Yeah. So from the figure you can see. Yeah. So which part I1 and I2. Yeah. Assume all currents and charges to be 0 at t. So initial value, yeah, given. The instant when the switch is closed. Yeah. All right. Yeah. So let's apply the Kirchhoff voltage theorem. Here, look at the component. The component, we have L component and R component, C component. Yeah. Yeah. These three different types of component. Yeah. All right. For the first circuit, first one, yeah. Yeah. I times I1 prime, 1. Yeah. L equals 1. Plus 4, yeah, R1, 4 ohms, 4 times. Yeah. Look at the direction. Yeah, here. When you look at plus minus, yeah, so you need to follow the, the direction of the current. Yeah. All right. I1, yeah, so the, clockwise direction. I2, counterclockwise, right? The opposite direction. So you need to use I1 minus I2. Yeah, different direction. Yeah. All right. Then E, so 12 volts, the first equation. Second one, yeah, second one this time, yeah. So you need to follow the direction of the current. Yeah. Second circuit, yeah. 6, yeah, R2, right? R2 times, 6 times I2 plus 4 times this time. I2 is the positive direction, right? Yeah, the same direction of this circuit. So I2 is the positive direction, and I1 is the negative direction. So I2 minus I1 times 4. Then the C part, 4 times, 1 over 0.25, right? So that's why 4. 1 over 1/4, so it's 4. Integral of I2. Yeah. And equals 0, because in the second circuit there is no E part, right? There is, so E part is 0. Yeah. Yeah? So we get this linear system. All right. Yeah. And the second one, you can see, the second one, yeah, integral. We have an integral, right? Yeah. So we need to take derivative on the second equation. First equation, we have the first order ODE. Yeah. Second one, yeah, we do not have the first order ODE, but after we take derivative, we get a first order ODE. Yeah. Okay. Yeah. All right. So we need to take a derivative. And the good thing is, think about, the good thing is, in the second circuit, there is no L component, right? Yeah. There is no L component. If we have L component, think about, then we will get a second derivative. We will get a second derivative. Yeah. Yeah. Okay? All right. So here, fortunately, yeah, but I think this example, try to do not make it too hard. Yeah. So do not put a L component in the second circuit. Yeah. All right. In this way, we have both first order ODE. So we get a system. Yeah. But both, yeah. So here, yeah. Yeah. All right. So, yeah. So replace, yeah, because I1, right? So here we replace I1 by this parenthesis. Yeah. All right. That simplification, after simplification, we get a second first order ODE. Yeah. So let's write them together so we get this ODE. But in this ODE, you can see the main difference of this one, you compare with the previous one, it's non-homogeneous. Yeah? So there is a constant term. Yeah. First equation 12, second equation 4.8. That means we have a G vector. Yeah. So this equation, we need to solve it. Yeah. It's the main difference with the previous one. Yeah. We need to solve this general equation. Yeah. Y prime equals A times Y plus that G vector. Yeah. So we need a non-homogeneous version. We need to find a way. How can we, adjust our solution to cover that G vector? Yeah. All right? Yeah. So that's the main technical question we need to solve here. Yeah. Before we get there, first, we can solve the homogeneous version first. Yeah. Yeah. So based on our experience, so first we want to solve the homogeneous version. Yeah. Second, remember the golden rule. I mentioned that golden rule, right? Yeah. So here you can see why people call the golden rule. It's so useful. So here, let me review that golden rule another time, right, related to this question. Our goal, we want to solve this non-homogeneous linear system. Yeah. So at this point, we feel a little hard for us. Yeah. So as a problem solver in this situation, we want to modify this problem to make it simpler. Yeah? Modify. How to modify? Ignore this G vector, right? So that's the obvious way we make the modification. Yeah. Golden rule tells us we can modify the original problem to get a simpler version, and we solve that simpler version first. Yeah. After we find the solution of the simpler version, then we consider the original problem. And we want to bridge the gap, because it's different from the original problem. But how do we apply certain technique to bridge that small gap? That idea, golden rule. All right, so here we can follow, take that strategy, apply that strategy here. Yeah. All right. First, let's consider. This is consider here, notation. So because here, when we do calculation, we want to choose appropriate notation. Here, capital J. Here you can see, in electric engineering, many times people use J to represent I vector. So there is one reason, because sometimes people need to use that I symbol, for complex, right? Imaginary special symbol in complex numbers. Yeah. So people want to, do not want to get confused. So many times, so the I vector, so use J symbol for the I vector. Yeah, because, it's not an imaginary symbol. Yeah. So that's something special. Yeah. All right. So here we use the capital J for this I vector. Yeah. So J prime equals, a derivative version. Yeah. So capital A matrix and little g matrix. Yeah. So we have this non-homogeneous linear system of ODEs. Yeah. All right. calculate the eigenvalues. Yeah. So calculate the determinant. Yeah. So this characteristic equation. Yeah. So, all right. The determinant, apply the formula. Yeah. After simplification. Yeah. So we get a lambda 1, lambda 2. Two eigenvalues. Yeah. Second, we need to calculate eigenvectors. Right? Yeah. So for lambda 1, we need to calculate our first eigenvector. Lambda 2, we need to calculate our second eigenvector. Yeah. All right. So there, we need to solve, a simple homogeneous linear system. Yeah. Because for the eigenvalue, for the eigenvalue, we know this determinant of this matrix is 0, right? So, yeah. When we calculate, remember this equation. You plug in eigenvalue 1, the determinant of that matrix is 0. Determinant of the matrix, this whole matrix equals 0. What does it tell you? If the determinant of this matrix, what does it tell you? Determinant of this 2 by 2 matrix. It tells you the two row vectors are linearly dependent, right? Yeah. If the two vectors are linearly independent, determinant must be non-zero. So now it's 0. The two row vectors must be linearly dependent. If linearly dependent, when we solve this, can we ignore the second equation? No, because the second equation does not provide any new information. The second vector basically just a constant multiple of first vector, right? Constant multiple. Here, can you see, let's say 0.8. The first vector, if we multiply 0.8, we get second vector, right? Yeah. So the second vector basically is a constant multiple of the first vector. So no new information provided from the second row vector, right? So then when we solve, we don't need to use the first vector, second equation. All right. From the first equation, remember, we want to take the simplest possible solutions. Yeah. Based on our observation, simplest possible. So when x2 equals 1, yeah, so 4 times 1 minus 2x1, x1 equals 2, we get 0. Yeah. So you can easily see we take the first eigenvector, this 2, 1, the simplest possible solution of the first equation. Yeah. Similarly, for the second eigenvector, yeah, so this is the first one. The second eigenvector, yeah, this time, yeah, determinant of this matrix must be 0. Yeah. So one of the two equations, they are linearly dependent, right? You can cross out one of the two. Yeah. If the second equation is easier, you can use the second equation, right? Yeah. Yeah. Because sometimes second equation is simpler than the first one, so you can cross out the first equation. You only need to solve the second equation. Okay. Yeah. All right. So then you can get it by observation. So you can get this 1, 0.8 vector, second eigenvector. All right. So you get you find these two eigenvectors. Yeah. All right. Then the general solution, but when you write the general solution, you write the homogeneous part. Yeah. Non-homogeneous part, we need to bridge the gap. So here, before we bridge the gap, first we need to write the general homogeneous part. Yeah. So that's JH, right? JH, yeah, homogeneous part. C1, then the structure eigenvalue times the corresponding E function, and C2, the second eigenvector, times its corresponding E function. Yeah. But that's the JH part. Yeah. Yeah. Then our next step, we need to calculate the JP part, particular solution. JP part. corresponding to that little g vector. Yeah. All right. Yeah. Find a particular solution. And this time we need to go back to the original equation with the g vector. This. All right. Here, we need to apply some simple technique here. Yeah. In order to get that g. All right. J prime, look at that J prime term. Yeah. Because remember, we have the solution of the part, homogeneous part. We have that solution. So we need to use that part to help us get the G part. All right. Yeah. So the JP should satisfy this equation. Yeah. We know JP should satisfy that equation. Okay. All right. Yeah. Here we need to make assumption to simplify. So here we need to use our imagination to make a reasonable assumption. Yeah. Based on our understanding of the structure. Yeah. How can you make some special assumption based on our understanding of the structure of this equation? So we can make some reasonable assumption. Yeah. How about we consider? Yeah. Because we have freedom, right? Yeah. We have freedom to choose JP. Yeah. So we apply our freedom. So here we consider this form. How about that? Consider JP is a certain constant vector. How about that? Yeah. Is it possible? Yeah. Because JP could be arbitrary form, right? So in the arbitrary form, we consider a very special form. Yeah? It's a constant vector. Yeah. Why this constant vector? There is a possibility. Yeah. Because when we take constant vector, JP prime is gone, right? JP prime is gone. Yeah? JP prime, derivative of constant, 0. Okay? So gone. Then derivative is gone, right? It becomes a times little a vector plus g equals 0. It's an algebraic linear system. So now let's plug in. Yeah, so constant vector, plug in, we get capital A matrix times little a vector plus g vector equals 0. Capital A is known, given. Little g, known, given. We need to solve for little a vector. That's simple, right? that is very simple. Yeah. So let's find this solution. Okay. All right. The question: is there a solution for this equation? Yeah. Because in this equation, we need to see if the solution exists or not. We want to answer this question: if the solution of this linear system exists or not. If the determinant of the coefficient matrix is non-zero, remember, see here I review linear algebra knowledge another time. Yeah. Under what condition the solution exists? Under what condition? Yeah. The determinant of A is non-zero, right? If the determinant of A non-zero, then solution exists. Yeah. Because when the determinant of A is non-zero, this A matrix is invertible, right? Yeah, remember last time, invertible. The inverse of A exists. Yeah. Then we can multiply inverse of A so we can find the solution. Yeah. All right, so let's do it in this way. Yeah. So here we calculate determinant of A. It's 1.6, non-zero. Okay, non-zero. Yeah. Then we know A matrix is invertible. Yeah. Next, we need to find A matrix. Find the inverse of A. Yeah. Yeah. Because we need to multiply the inverse, A inverse. Yeah. So there is another question: how to find the inverse matrix of A? Yeah. Fortunately, our A matrix is a 2 by 2 matrix. Yeah. There is a simple formula. We can use the simple formula for its inverse. Yeah. Yeah. Here, I can give you that simple formula. Now we need to solve this linear system. You can see if we multiply A inverse, both sides, A inverse, we can get A immediately. Yeah. A little a equals negative A inverse times G. Yeah. So we only need to find the A inverse matrix. Yeah. All right. Yeah. How to calculate inverse of 2 by 2 matrix? Yeah. Formula of 2 by 2 matrix, it's inverse. Yeah. A inverse equals 1 over its determinant. Okay? Then 2 by 2, the entries, we just change on the main diagonal, we need to switch the two elements, main diagonal. Yeah. On that diagonal, yeah, so negative. Yeah. We do not change, but we need to change the sign. Yeah. That's the inverse matrix formula. Yeah. Now let's apply that formula. We calculate A inverse. So this is the A inverse. A inverse, then you multiply that G, you get a JP A vector is 30, JP vector. Yeah. So in this way, yeah. So you get a JP, yeah. So you get a whole solution. Okay? Yeah. So here, yeah, we use some basic knowledge of linear algebra. Yeah. So we can solve this non-homogeneous linear system. Yeah. Yeah. All right. Yeah. So then, general solution. Yeah. Yeah. The JH part and then JP part. Yeah. C1, C2, we need to use our initial condition to find C1, C2. Yeah. All right. Yeah. So this equation, C1, C2. Yeah. So then the final solution. Yeah. We can write the final solution. Yeah. Like that. All right. Yeah. So after this example, yeah, so we need, yeah, the method actually very simple. Yeah, the method. Yeah. The JP can be a constant vector. Yeah. Very simple. Yeah. All right. Yeah. Yeah. So you just write the I1, I2. Yeah. Okay. All right. Yeah. But here, yeah. After this example, we need to think about, a few places. Yeah. One place is we need to think about if we have that L component in the second circuit, then it's not a linear system, right? The second order ODE. Yeah. So that is one. Yeah. Yeah. But in that case, we know Laplace transform. We can do it easily, right? Yeah. Yeah. Because in that case, second order ODE in our Laplace transform, just S squared, right? From S to S squared. Yeah. So if you see second order ODE, yeah. So probably the easiest way. So you apply Laplace transform. Yeah. Yeah. The first order you can also apply Laplace transform, right? Yeah. But if you apply a Laplace transform, then you basically solve algebraic equation. Yeah. Yeah. So it's a different way. Yeah. You can also solve it, and it is not very hard. Yeah. Yeah. All right. So that's the part A. So now we go to part B, so we can cover some topics, preparation topics. Part B, we want to study the non-homogeneous linear system of ODE. Yeah. So we want to study more cases. B.1, constant coefficient system of ODEs. Yeah. All right. Yeah. So first, so I want to talk about some basic knowledge of linear system of ODEs with constant coefficients. The simplest case. N-dimensional case this time. All right. Yeah. So we need to use the notation. Consider a solution with the form. So based on our experience from part A, we know the basic structure. We can describe one typical solution. Here, this is a typical solution. Y equals x vector, eigenvector, right? So x vector times e to the lambda t. So that's the typical solution. Should be in this form. All right. Then we take a derivative. So we get a lambda chain rule. Then equals, because based on the original equation, right? Y prime equals a times y. So this should be true. So then, because e function can never be 0, right? E to the lambda t. So this, it's a non-zero function we can cancel out. After we cancel out the e function, we get ax equals lambda x. Then, based on our knowledge of eigenvalue, eigenvector, so we can see it is an eigenvalue problem. All right. So now, regarding the eigenvalue, because eigenvalue problem, actually it's a very complicated problem. So if you want to study the whole problem completely, it is very complicated. So for us, we only want to study relatively simpler part of this eigenvalue problem. So here we make some key assumption. Under the certain key assumptions, that this problem is not hard. So we can handle easily. All right. So what are those assumptions? All right. The key assumption is what we need. A matrix has a linearly independent set of n eigenvectors. Actually, this assumption is very important. All right. So let me describe the whole situation here. If we do not have this key assumption, if we do not put this key assumption here, then for some relatively bad matrix, if some relatively bad matrix, then we may not be able to find a set of n eigenvectors that are linearly independent. So that could happen. That could happen. In that one, so the structure of the eigenvectors, could be very complicated, linearly dependent. So we couldn't find linearly independent. But if we couldn't find linearly, then we cannot get the basis functions for our linear system. We cannot. We cannot represent the whole general solution. We cannot. So that's the reason. We want to make this assumption, then we can do everything we need to do. All right. So then this assumption, how realistic it is, we need to answer this question. Because if you make too much assumption, too restrictive, because when we make assumption, we restrict ourselves. If you make it too restrictive, then a lot of engineering problem cannot be covered, right? So, but the situation is, for this assumption, most of our engineering problem we can solve. So most applications have this property. Real world applications, all right? Have this property. So usually for relatively good matrices, we have this property. For some very bad matrices, some matrices, the structure very bad, then we may not have that property. All right. Now here there are some simple type of matrices that have this property. The first type, where A has n different eigenvalues, the simplest case. So when you calculate a characteristic equation, when you calculate the roots, there are n different roots. We call it simple roots. Okay, so your characteristic equation has n simple roots. Then this condition is satisfied automatically. Okay, so we can prove. So all the eigenvectors for n simple eigenvalues must be linearly independent. It can be proved easily. All right. So that's the first type, n different. Second type, A is a symmetric matrix. Asymmetric matrix. So that's another special type of matrix. Symmetric. A equals A transpose. A equals A transpose. So what's that? So if I draw a matrix with respect to the main diagonal, okay? So the entry, if two entries, why cannot? Two entries are symmetric with respect to the main diagonal, they must be the same. Okay? If we use the formula to write, little a jk equals little a kj. So if you switch row and column indexes, row index and a column index, you switch the same. So symmetric. So if it's symmetric, so here, and the skew symmetric, so it's not symmetric, but skew. What's the skew? Negative. You put a negative sign. So if you switch row column indexes, but you need to put that negative sign. For these two types of matrices, then that property, we have this property. So what property? A has a linearly independent set of n eigenvectors. That property. All right? And in second case and the third case, symmetric, skew symmetric, these two cases we allow the same eigenvalues. Yeah. The first case, simple all the eigenvalues must be different, right? For case 1, all the eigenvalues of our characteristic equation, all of them must be different. But for the second and the third, symmetric, skew symmetric, yeah. If some eigenvalue has multiplicity, more than 1, it is allowed. It's okay. Yeah. That means even if certain eigenvectors, certain eigenvalues have multiplicity more than 1, we can still find linearly independent eigenvectors. Yeah, we can still find linearly independent eigenvectors. Yeah. So that's the type of matrices we consider. Yeah. Otherwise, the situation could be very complicated. Yeah. All right. Yeah. But other than these 3 types of matrices, you can imagine it is possible there exists some matrices not in these 3 types. Yeah, not in these 3 types. But those matrices can still have n linearly independent eigenvectors. Yeah, it's possible. Yeah. But just how to describe, right? So what are those matrices? How to describe? Yeah. Still, it's possible they have n linearly independent eigenvectors. Yeah. Yeah. All right. Yeah. Yeah. So here, sorry. Yeah. 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 So that's the, yeah. So the key assumption we need. Yeah. And for the second case and the third case, symmetric matrix, skew symmetric, yeah, because eigenvalue with multiplicity more than 1 is allowed. Yeah. So I may think about, so if I can find a simple example, yeah, corresponding to that case. Yeah. So one of the eigenvalues has multiplicity more than 1. Yeah. So I try to find a matrix 3 by 3. Yeah. A should be a 3 by 3 matrix. Yeah. 3 by 3 matrix. So you have 2 eigenvalues, but one eigenvalue has multiplicity 2. Yeah. The other multiplicity 1. So that one has multiplicity 2, but you need to find 2 eigenvectors that are linearly independent. Yeah. So in that way, so I may try to find such an example for you. Yeah. So you can understand this case better. Yeah. All right. Basics of solutions and the wrong scale. Yeah. So that's just straightforward extension. Yeah. Yeah. Eigenvalue problem. Yeah. So we have eigenvectors. Yeah. So here n different eigenvectors. Oh, not just different. N linearly independent eigenvectors. We need. Yeah. Then we want to represent our general solution. Okay? Yeah. All right. So our key assumption, A has linearly independent set of eigenvectors. Yeah. Fundamental matrix. Yeah. So the concept we used before, but this time, because each y solution vector, we have the structure. Yeah. Yeah. So eigenvector times E function. Yeah. So our Y matrix can be represented. So here we need to use that form. Yeah. Matrix of eigenvectors. We need to use eigenvectors. Capital X. Yeah. Capital X is the matrix of all the eigenvectors. Yeah. We want to use this matrix to represent fundamental matrix, capital Y. Okay? Yeah. Yeah. So capital X is invertible and the determinant of X non-zero. Can you see that easily? Yeah. Yeah. Very easy. Why X invertible? Because these n vectors are linearly independent. N eigenvectors are linearly independent. Yeah. So capital X matrix is invertible. Determinant of X is non-zero. Yeah. All right. Now relationship between X and Y. What's the relationship? Yeah. Relation very simple. So Y equals this form, substitution, but this we want to write a matrix multiplication. This expression we want to use matrix multiplication to write it. Yeah. Yeah. Linear, yeah. So here, another way to see why these solution vectors are linearly dependent. So let's write Y in another form. So this Y equals capital X matrix times E function. We arrange all the E functions in a diagonal matrix. This is a diagonal matrix. Yeah. Put all n E functions at a diagonal, n diagonal entries. Yeah. So it's a product of two matrices. Yeah. By matrix multiplication definition, we can see easily, right? So you do, row column, row column. So matrix multiplication. Yeah. So you can get this product easily. All right. Then we use capital lambda represent this diagonal matrix. Capital lambda. Yeah. Okay. Yeah. E function. We know E function can never be zero, right? So all the diagonal entries are non-zero. Now, all the diagonal entries are non-zero. E function can never be zero. So this capital lambda matrix is invertible. Yeah? Because it's determinant. What's the determinant? Determine the product of all these E functions. Its determinant is non-zero. So this lambda function is invertible. All right. So determinant of product of two matrices. Yeah, here. We want to look at the determinant of capital Y. But determinant of capital Y equals determinant of capital X times determinant of capital lambda. Yeah. So there is a general property. Yeah. Determinant of product of A times B equals determinant of A times determinant of B. Yeah. It can be proved. Yeah. It can be proved. So here we apply this property on capital Y. So you can get determinant of capital Y equals determinant of capital X, non-zero, times determinant of capital lambda, also non-zero. So the product of these two non-zero numbers also non-zero. So that's why determinant of Y is non-zero. So these n Y vectors must be linearly independent. All right. So then Wronskian, just determinant of Y, based on the definition, the Wronskian. Here, the n solution vectors, n linearly independent solution vectors. Yeah, so we calculate the Wronskian. Yeah, determinant of the matrix with these n vectors. Yeah, that's the Wronskian. All right. Yeah. Yeah, so equals this product of X and lambda by that property equals determinant of X times determinant of lambda. Non-zero, non-zero, yeah, yeah. So not E function, the determinant of lambda is an E function, non-zero. Yeah, yeah. So the determinant of x times E function, non-zero. Yeah. So that's the reason we can see linearly independent. Yeah, yeah. Just some basic property. Yeah. You know, some general formula. Yeah. Sometimes we need to use. Yeah. All right. The general solution. Yeah. At the end, we need to write the general solution. Yeah. So little y, general solution is like this. Yeah. But we may like to use the matrix multiplication form. The matrix, yeah. So you have, you know, capital X matrix, right? Yeah. You know, yeah. Yeah. Capital Y, yeah. So the capital Y times that C constant vector, yeah. C1, C2. So you put it in a column vector, yeah. So still capital Y times C vector, the general solution. Okay. All right. Yeah. So that's the preparation, yeah, the part. Yeah. So we get familiar with the notations, terminologies, you know, the setting. Yeah, we need to use. Yeah. So later when we do discussion, so we will use the language we prepared here. Yeah, yeah, yeah. So the next time we will try to solve non-homogeneous. Yeah. So the more general case of the non-homogeneous linear ODE. Yeah. All right. Yeah. So that's it. Yeah. Yeah. After 2 classes next week, I will give you a third homework assignment. Yeah. Third. Yeah. So we 2 more. Yeah. Let me see. Oh.